This is section 10.2. We have displacement and distance traveled. Recall that when a particle moves along a line with velocity v of t, the displacement or net distance traveled from time t equals a to t equals b is given by the integral of the velocity. What this is saying is when you take the integral of velocity, you are finding the displacement. You're not finding the position. We can use displacement to find the position, while the total distance traveled in the time interval is given by the integral of the magnitude of velocity. When a particle moves in the plane with velocity vector v of t, displacement and distance traveled can be found by applying the same integrals to the vector v, although in slightly different ways. We have a definition: displacement and distance traveled. Suppose a particle moves along a path in the plane so that its velocity at any time t is given by this velocity vector, where v1 and v2 are integrable functions of t. The displacement from a to b is given by these vectors. This is the displacement of the particle, so both of these are displacement. The preceding vector is added to the position at time t equals a to get the position at time t equals b. If the position of the particle at, let's say, t equals 0 is 3, 2, and you want to find out the position of the particle at t equals 4, then the x-coordinate is going to be the integral from 0 to 4 of the x part of the velocity vector, so integral of v of t, but that's the x part, dt, and then that'll be the displacement, and then we'll add 3. If you want to find the y-coordinate, you do the same thing on the y part of the velocity vector. So we integrate from 0 to 4 of v of t on the y part, and then in this case we would add 2 to find the position. The preceding vector is added to the position at time t equals a to get the position at time t equals b. That's exactly what we've done. They're saying take the displacement and add on the position at time t equals 0. The distance traveled from a to b is the integral of the magnitude of velocity, or in other words, the integral of the speed of the object. In exercise 37 to 40, the velocity v of t of a particle moving in the plane is given, along with the position of the particle at time t equals 0. Find a, the position of the particle at time t equals 3, and b, the distance the particle travels from t equals 0 to 3. They're giving us the position at, this is when time is 0, and we want to know the position of the particle when t is equal to 3. And that's going to be a point, so we integrate from 0 to 3 of et minus t dt, but then we'll add on 1, and that comes from this value right there, the x value. The y-coordinate is going to be the integral from 0 to 3 of e to the t plus t dt, and plus 1 also, but that's actually coming from this one right here, and they just happen to be the same value. The integral of e to the t minus t is e to the t minus 1/2 t squared, evaluated from 0 to 3, and then we'll add 1 to that. The integral of e to the t plus t is e to the t plus 1/2 t squared, and we will evaluate that from 0 to 3. And add 1 to this one also. We have e to the third minus 1/2 times 9, and then plus 1. And we'll have e to the third plus 1/2 times 9, and plus 1 also. The rest of this will be decimal values. Let's use our calculator to get that. We have e to the third minus, well, 9/2. Oops, I got to clear that. Clear. Yeah, it's not working with it. That's weird. This will be decimal values, so let's use a calculator to answer this one. We have e to the third minus 1/2 of 9, and then plus 1. And our answer is 16.586. So that's equal to 16.586, and the y value is, the only difference is the plus there, so let's get that entry back in there and make that a plus. Enter. We get 25.586. 25.586. A particle moves in the plane so that its position at any time t from 0 to 2 pi is given parametrically by x equals sine t and y equals cosine of 2t. A. Find the velocity vector for the particle. That's the derivative. So in part A, we just have to take the derivative and write it as a chevron because it's a vector. The derivative of sine t is cosine t, and the derivative of cosine 2t is negative 2 sine of 2t. Part B, for what values of t is the particle at rest? In order for the particle to be at rest, both the x part of the velocity vector and the y part of the velocity vector must both be 0 at the same time. If we had this particle and it was traveling along the Cartesian coordinate system, the y-coordinate of the velocity vector could be 0. In other words, the particle is not going up or down. And then if it turned and went straight up, then the x-coordinate of the velocity vector would be 0. So you can have them be 0 separately, and the particle is still moving. So I need the x and the y to be 0 at the same time. Now remember, we're going from 0 to 2 pi here. So we want to know when cosine of t is equal to 0. That means t is the inverse cosine of 0. So t is equal to pi over 2 and 3 pi over 2. That's the two places where cosine is 0. This equation is a little bit more complicated. We have negative 2 sine of 2t equals to 0. And if we divide both sides by negative 2, we have sine of 2t equal to 0. And then 2t is equal to inverse sine of 0. Let's answer this. On one trip around, where is sine 0? Sine is 0 at 0 and pi. But if we divide by 2, we get 0 and pi over 2. We can keep going with this answer. And 0, pi, that's 0 pi, 1 pi, 2 pi. 2 pi would give us a t value of pi when we divide by 2. 3 pi would give us an answer of 3 pi over 2, and 4 pi would give us an answer of 2 pi. So there's where t is between 0 and 2 pi. That would make this y-coordinate 0. T has to be from 0 to 2 pi. Now we just have to match them up. T for cosine is pi over 2 and 3 pi over 2, and we actually have the same values for the t's for the y-coordinate, pi over 2 and 3 pi over 2. So that's the answer to letter B. The letter B's answer is pi over 2, 3 pi over 2. Let's look at letter C. Write an equation for the path of the particle in terms of x and y that does not involve trigonometric functions. In other words, we need to try to eliminate t. We have x equals sine of t, and we have y equals cosine of 2t. What I notice in this one is we have a double angle formula for cosine. Now, what I do have memorized is that cosine squared of t minus sine squared of t is equal to cosine of 2t. And then I want to replace with sine of t, so I want to get rid of this cosine squared. So y is equal to 1 minus sine squared t. That comes from the Pythagorean identity. And then minus sine squared t. So y is equal to 1 minus 2 sine squared t. And x is sine of t. So now I can make this replacement 1 minus 2 x squared. If I square both sides, we get x squared is sine squared. Make that replacement, and now the t is eliminated. That is your answer right there. In letter D, we're asked to sketch the path of the particle. And so yes, you just have to plug in sine of t for x and cosine of 2t for y, and there's the path of the particle. And if this was a test, you just have to jot this down. A particle moves in the xy plane so that its position at any time t from 0 to pi is given by this function, and y of t is 3 sine t. Sketch the path of the particle in the xy plane below. Indicate the direction of motion along the path. Let's do that on the calculator. I need to put my calculator into parametric mode. There we go. And y equals, and we need x squared divided by 2 minus the natural log of 1 plus t. 1 plus t. And then y is 3 sine t. 3 sine of t. Enter. And let's look at our window. We're going from 0 to 2 pi. That's good. We just want 0 to pi. This would be good because we're graphing a trig function, but the problem literally says go from 0 to pi. So let's do that. Let's put pi in for the maximum for the t value. And 0.13 is fine for a step. The smaller we make that number, the slower the graph. And if it graphs it too fast and we can't see which direction it's going, we'll just make that a smaller value. Negative 10 to 10 is probably a little too wide. Looks like I have negative 3 to 3 set up for this. Let's try, how about negative 4 to 4? 1 by 1s is fine. And then maybe we go negative 4 to 4 on the y's. And if this doesn't fit, we'll just change it so that it will fit. Let's hit graph. And that's slow enough so that I saw that the path started here and then looped around. Let's try to imitate that a little bit. We'll copy it. We're here. Looks like we're at 3. And then looks like we are a little past 1, 2, 3. A little past 3. So maybe it ends right here. So we're looping up and then coming back down like that. And the direction of the path as it was graphed is this path right here, and we'll indicate that with little arrows. At what time t, 0 to pi, does x of t attain its minimum value? We need x prime of t. So we need the derivative of x if we're going to minimize x. The derivative is, well, we have t squared over 2. The derivative of that is multiply by 2 and then reduce the power by 1. So we have 2 over 2t. Let's jot that down, which is just t. And then we have minus 1 over 1 plus t. Minus 1 over 1 plus t. We want to know where this is equal to 0. And we have 0 equals t minus 1 over 1 plus t. Let's use the calculator to find that out. In order to do that, we're going to have to get out of parametric mode. We just want function mode now because we're working with one equation. We have y equals, and we have t minus 1 divided by 1 plus t. Let's graph this. Let's go to the standard, zoom 6. And it's the first 0 that we come across on the positive side. So we want that one right there. So let's go calculate. We want a 0. And we are now to the left. Let's go to the right of the 0. And then we'll back up and we'll say we want that 0 right there. Press enter, and it is 0.618. So t equals 0.618. At what time t does the x of t attain its minimum value? There's the time right there. What is the position of the particle at this time? I need to plug 0.618 into x of t and y of t. If I go back to parametric mode, those two functions should be in there still. Hit y equals, they're still in there. Hit graph, there it is, graphed again. And we can calculate just values. And I'll plug in 0.618. Press enter, and its position is, let's scroll back down here. Its position is negative 0.290 and 1.738. At what time t from 0 to pi is the particle on the y-axis? We know that a particle is on the y-axis when the x-coordinate is equal to 0. So we have x of t is equal to t squared over 2 minus the natural log of, I believe it is 1 plus t. It is 1 plus t. We want to know where this is equal to 0. Let's use our calculator to do that. We need to go back to function modes. We're kind of bouncing back and forth on this problem. We have y equals, and I need x squared divided by 2 minus the natural log of 1 plus t. 1 plus t. Let's graph that, and then we'll try to find out where it crosses the x-axis. And it looks like somewhere in there. We could zoom in a little bit. Let's do that. Let's zoom box. We'll scroll over, go down, get the other corner. There it crosses through 0, and there's the first place where it crosses the x-axis after 0. So let's calculate the 0. Enter. Scroll over, press enter, back up a little bit, and the t value is 1.286. So t equals 1.286. Does that answer the question, though? At what time is the particle on the y-axis? It does answer the question. Finally, find the speed and the acceleration vector of the particle at this time. Speed is the magnitude of the velocity vector. And at no point did we find the derivative of y. We found the derivative of x, but we need the derivative of y as well. So the velocity vector is t minus 1 over 1 plus t. We need the y coordinate of the velocity vector, which will be 3 cosine. We need to take the derivative of y. 3 cosine of t. We're finding the speed and the acceleration vector of the particle at this time, which means we'll plug in 1.286 into the square root of t minus 1 over 1 plus t squared plus 3 cosine of t squared. And we'll evaluate that when t is equal to, and maybe we use more than 3 decimal places. How about 1.285887? We'll use all of them for a more accurate answer. Let's use a calculator for that, of course. We can quit out of this. We're taking the square root of x minus 1 divided by 1 plus x, and all of that squared, plus 3 cosine of x squared. This is going to work because the last x value we had, if we want to go back to the graph actually, our last x value we had was this x value right here. So on the home screen, when I press enter, it'll give a value, and it's 1.196. 1.196. And finally, they want the acceleration vector. We have to take the derivative of the velocity vector. We have 1, and there's the derivative of t. Then we have 1 plus t to the negative 1. So we have 1 times 1 plus t to the negative 2. 1 plus 1 over 1 plus t squared, comma, negative 3 sine of t. And we'll evaluate that when x is 1.285887. Now my calculator is still holding that 1.286 into it. I should be able to plug in, just type on the calculator 1 plus 1 divided by 1 plus x squared, and it should give me an answer, which is 1.191. 0.191. This is the acceleration vector now when t is this value. Then we need negative 3 sine of t, or x in this case. Negative 2.879.